Hey guys, so today we're going to be going over how you can find the discontinuity or continuity of a function over a domain. These questions will include simple questions such as y equals x plus 2 and y equals 3x squared over 2 minus x. But it will also include some trickier questions with trigonometric functions such as sine x, cos x, and tan x. Another thing to note, these questions will involve limits, so if you haven't already checked out my other video on limits, make sure to do so in one of these two corners right now. But if you already know that, then without further ado, let's get started. Alright, so the main concept. The main concept would be that let's say you have a graph, and let's just put it right over here. This is the graph, this is the y-axis, the x-axis, and the origin we can label with the 0. So over here, these are a few, let me do some tick marks. There. So that is our coordinate plane. Let's say that you have a function like that, all right? You have a function like that and it keeps going on forever in that direction and in this direction as well. It doesn't matter what the function is for now, it's just an example, so you get the main concept. The main concept essentially is that let's take a point over here and let's name this A. So A is essentially an x-coordinate because it's on the x-axis. So the y-coordinate, if this is f of x, this function is f of x, the y-coordinate will be f of A. The y-coordinate will be f of A. So now, this limit will essentially this function will be continuous when two conditions are met. The first condition is if the limit as x tends to a of f of x actually exists. Now this is one condition. So we can say, in order to actually show you guys what this actually means, let's say we have another coordinate plane. Say we have a coordinate, we have a coordinate plane over here. Let me just do a rough sketch. All right, and then we have a graph like that, and it goes over there, goes here. And this is our point. So, but in many of the questions, you won't actually see a point. Instead, you'll see a hole in the graph. So therefore, the limit as x tends to a, oh, this is a by the way, and this is, let's say this is g of x, then this is g of a. So therefore, the limit as x tends to a of g of x this time does not exist. So this represents discontinuity. That's rule number one. So if you already have a hole in the function, you automatically know it's not continuous at this x equal a point. Now, the second rule would be that x, the limit as x tends to a of f of x should equal f of a, and that it should be true. So if these two conditions are met, then at that particular point, your function will be continuous. So let's take an example for this. We'll use this example once again. Let's say that at f of a, you have a point here. So we already know that according to rule number one, this is not continuous, but let's see rule number two. So rule number two is as the limit x tends to a of g of x, we're using this graph, of g of x equals g of a is true. So if this is true, that means we have a continuous function. But as we see, the limit as x tends to a of g of x, it zones in on this point. If you follow the graph from both the right and the left, it zones in on this point. However, g of a is a completely different point since it's plotted like two numbers, let's say 2 units above this hole in the graph. So none of these conditions exist for this graph. Therefore, this graph is discontinuous. However, if we have a graph such as this graph where there is a point on the f of x, you can see that the limit of f of x exists since there's actually a point. And we know that according to the second condition, as limit x tends to a of f of x equals f of a, we see that, as the limit as it comes from the right side and the left side, it zones in on f of a. And we know that f of a is simply equal to this point since there is no hole in the graph. So therefore, this one and this one is true for this. So this graph is continuous. All right, let's dive into our first question. Our first question is f of x equals x minus 1 when x is not equal to 0, and f of x equals 2 only when x equals 0. And the question is asking, is this f of x continuous at x equals 0, yes or no? Now, we have our two properties of a continuous function right here, so let's use that to help us see if this is continuous or discontinuous at x equals 0. So first, let's look at the first property. We see that the limit x tends to a of f of x exists. So let's see if this property is true for this, or if the limit actually exists for this question. So we see that f of x, this is the solution. I see that f of x equals x minus 1. Let's take that. Because you see here, x is not equal to 0. And it says limit as x tends to a in this case is 0. So in order to describe it better, we essentially want to see where f of x zones in, what point f of x zones in on, so as x approaches 0. So here I took a, so this is like a general explanation of limits. So as it's approaching the right side and the left side, what is that point that f of x approaches? That's what we're trying to find out, but in this case, a is 0. So that's what we are going to do. So we see that x is not equal to 0. That's why we're putting 0 in this essential expression. So if we put f of 0, we get 0 minus 1, which is just negative 1. So as x tends to 0, f of x approaches negative 1. Now, we have that the limit actually exists. So if it doesn't exist, you'd probably get something like negative infinity or infinity, but we got a concrete value. So this proves that it does exist. But now we have to see the second condition. So the second condition would be limit x tends to a of f of x equals f of a is true. So we see that we have f of a, and we essentially already found the limit as x tends to 0 of f of x, which is just negative 1. So we can also write this as limit x tends to 0 of f of x equals negative 1. We can also write it like this. So let's try to find f of a. We know that a is 0, so we have f of 0. And we know that f of 0 is 2, because when x equals 0, f of x equals 2. So we can write 2. Now this says that limit x tends to a of f of x, is that equal to f of a? Let's see, is negative 1 equal to 2? Well, we know that negative 1 is not equal to 2. So this means that this function is discontinuous. So it's discontinuous at x equals 0. So we're going to say no, it's not continuous at x equals 0. To make a bit more sense, let's actually graph this. All right, so this is how the graph of f of x looks like. We know that at x equals 0, f of x equals 2, so there is our 2. And we know that for any other value except x equals 0, we will graph it x minus 1. So let's say we have 1. 1 minus 1 is 0. That's how we got this point right here. If we put 2 in here, we get 2 minus 1, which is 1. So that's how we get this point. It's not accurate, guys, that point. But however, if we put 0, we get 0 minus 1, and that's negative 1. So if we put 0 and then minus 1, you see there's a hole in the graph, meaning that this function approaches minus 1, but its actual value is 2, because at x equals 0, f of x equals 2, and that is explicitly given. So also by graphing, you can see that this is discontinuous, as we saw in the main concept. So f of x is not continuous at x equals 0. All right, so question number 2. Question number 2 states that f of x equals x squared when x is not equal to 0, and equals 1 when x equals to 0. Now we have to see if it's continuous at x equals 0, yes or no. So let's see. We have our two properties again to determine if f of x is a continuous function. Let's start with the first property. First property states that as limit x tends to a over here is 0, of f of x actually exists. So that's saying limit, this is the solution, limit as x tends to 0 of f of x actually exists. Let's solve this. So this is also limit as x tends to 0. F of x, we know that as x tends to 0, we take this one, x squared, because we will use this part for f of a. So then we get 0, since we just replace 0 in for here. So it does exist, we get 0, so we say that condition number 1 is true. We also somewhat completed condition number 2, the left side of condition number 2, since we found the limit as x tends to 0 of f of x. So now for this side, we know that, it's right here, we know that f of 0, this is x equals 0, so f of x is 1 equals 1. So now we have to see, is the left-hand side and the right-hand side equal? Is the left-hand side and the right-hand side equal? Well, 0 is not equal to 1. So we can say that this is a discontinuous function, meaning that it is not continuous at x equals 0. In addition, we can also graph f of x like I have done over here. You see that this is essentially f of x. So it is x squared, meaning that it's going to be a parabola opening up. And we know that at x equals 0, f of x is 1. So that's where this point comes in. And let me make this a bit bigger. All right, so now you see that there is this big hole in the graph. And that is because over here, if we put 0 in here, you get 0. So it's approaching 0. As x tends to 0, f of x is approaching 0. That's why it's slowly approaching 0. But that doesn't mean it equals 0. Instead, it equals 1 because we put 0 in for f of x and we got 1. And that's why there is a hole in the graph. And whenever there's a hole in the graph, you automatically know that the graph at that point, in our case, 0, x equals 0, it is discontinuous. So our last question for this video would be f of x is equal to sine x over x when x does not equal 0, and 1 when x does equal 0. And once again, they're asking us if it's continuous at x equals 0, yes or no. All right, so we do the same exact procedure. Let's label this the solution. And now we have to see if the limit of f of x actually exists at x equals 0. We can do that limit as x tends to 0 of f of x. That is equal to limit x tends to 0. And we use this one. So we get sine x of x over x. And in my previous video, I said that limit x tends to 0 of sine x over x is always going to be 1. And now we can move on to our second condition. Our second condition is essentially this, which we already did. And we found out that it exists and the limit at x equals 0. Now we have to find f of 0. So f of 0, we replace, well, it's f of x and at x equals 0, f of x is equal to 1. So we say that this is 1. So does the left-hand side equal to the right-hand side? Does the left-hand side equal to the right-hand side? Well, yes, 1 equals to 1. So we can say that f of x is continuous at x equals 0. Hey guys, so that was the end of the video. I hope you learned how to find if a function is continuous or discontinuous at a certain point. Now these questions were fairly simple, I would say. Just keep practicing on your own. I will make another video showing how you can find the discontinuity and continuity of more complex functions. And that video will have multiple problems. This was just a beginner-friendly introduction to discontinuity and continuity. But stay tuned for that, and I will see you next time. Bye, guys!